So here I have just the first of two protecting group oriented problems. This first one has 4 steps, and recognize the little note I have off here to the side about step 1, but go ahead and try to figure out as many steps as you can, and then we will talk about the answers. So in the first step, we have methylamine, and the the takeaway from the step 1 having no solvent, what that really means to us is that there's probably going to be an excess, more than one equivalent. So it's just no solvent is another way of saying it's very concentrated, or there's an excess. So the first methylamine is going to come over. It's going to open up the ring by attacking the carbonyl. So opening up the ring, we'll have that ester oxygen, the negative charge right here. We still have that alcohol, and then the carbonyl that is now an amide. So if you're wondering if a methylamine comes and pulls off this proton from the alcohol, you're absolutely right, it will. It'll just put it back on, because in the first step, pulling off that proton doesn't really do anything for us. You could maybe suggest some sort of thing happens when you do that, but anything that you do with that oxygen with a negative charge is just going to be reversible. So it's another good reason, say no solvent. Maybe you'll pull off the proton, and another one will give it right back. So anyways, this is the first answer for step 1. Going on to step 2, TRCl, that's just triphenyl methyl chloride. So it's a really big, bulky protecting group. So it's used to protect alcohols. And in this case, we have, although it doesn't quite look like it, this is an alcohol, right? And maybe if you wrote this step 1 with the oxygen being protonated, that'd be just fine. I left it unprotonated right here, so it's a little bit easier to see what's going on. But either way, you'd have this oxygen attacking the methyl part of the triphenyl methyl chloride, kicking out the chloride. So we end up getting this sort of thing attaching. And it is a selective reagent, so we don't see it protecting the other alcohol. We can explain the selectivity because it's so bulky. So triphenyls, that's 3 benzene rings, plus a methyl group that's attaching them. There's a lot of carbons right there. So trying to put that big group next to a carbonyl, and it's also on the inside of a long carbon chain, is probably going to be difficult. So this is more selective here. The PY is just pyridine, DMF is just your solvent. So going on to step 3, that's lithium aluminum hydride in step 3, and THF, just your solvent. The purpose of lithium aluminum hydride here is going to be to reduce our carbonyl. So we know that if we throw lithium aluminum hydride, a strong source of H-, and with an amide, we can expect the amide to be reduced all the way down to the amine. So that's what we'll see. So we still have this thing going on. And there's your amine, just like that. And I could draw in where the H's have gone. I guess I should also add that if you're going to throw in a strong source of H-, use it as a nucleophile, it's also going to have an opportunity to act as a base. So it could pull off the amide H, but it'll be more likely it pulls off the alcohol H. So if it pulled off that H, you'd be left with this sort of thing. If you also suggested it pulled off the amine H, that's fine too. It is less likely. That's okay, because in our final step, so step 4, methanol and water. It's kind of a crummy suggestion of a source of a proton. That's all it is. So if you add methanol and you have something that's wants a proton, methanol will very easily give it up. So that will solve the anion issue that we had previously. And so that's why I said it doesn't matter if you suggested deprotonating the amine in step 3, because in the end, you'll always end up in the final product, even if you deprotonated both. So that's the first one. Let's go on to the second problem I have. So in this problem, we have just one more step, it looks like, but it's still working with protecting groups. So why don't we give this one a try to go through 1 through 5, and then we can work through what's going on in each step afterwards. So in the first step here, so number 1, we have TBSCl with some imide and DMF. So DMF is just our solvent. TBSCl, sometimes a few textbooks might refer to it as TBDMSCl. It's the same thing. It's just tert-butyl dimethylsilyl chloride. We know that to be a good protecting group for alcohols. The imide here, we're just going to kind of treat it as a kind of crummy source of a base. If you're curious what an imide looks like, a generic form would be something like this. And so you can tell it's not going to be an amazing base, but if we needed it to, it could do that. So going on, step 1, we again know that this is just going to do a good job of protecting our alcohol. So if we redo everything, the acetate isn't going to change at all. Our alcohol will, and we'll get this sort of thing going on. So in step 2, we have potassium carbonate, which is a base, and then we have methanol, which is our solvent, and it's also going to be our reagent that's going to be doing the work here. So if you have potassium carbonate with some methanol, you'll pull off a few of the methanol's protons. When you do that, you now have a better nucleophile. So let the nucleophile attack the acetate. When you attack the acetate, you'll do a Fischer esterification, and you'll let the bigger portion fall off. So that becomes easier to see when we write it down what's going on. So there's your OTBS, and still on a wedge, now just an alcohol. We could also write what fell off if that's, that could be a nice thing to visualize. So the thing that fell off would be this stuff. So that's what just fell off. In step 3, we have PCC, so we know that to be a selective oxidizer. And we have, there should be a 2 right here. So this is methylene chloride. There should be a 2 right there. So methylene chloride is just a really heavy solvent for us. PCC, we know is selective oxidizer, so let's oxidize the only thing that we can oxidize here, and that's going to be our alcohol. So oxidizing that alcohol, we now have a conjugated pi system, so that's nice for stability, and OTBS right there. So in step 4, we have methyl lithium, and then diethyl ether, and we're running this cold. So in step 3, methyl lithium is a very good source of carbon nucleophile. So we can also kind of think of it as a Grignard reagent, if that's helpful. So let the methane attack the carbonyl. And since it is a hard nucleophile, it'll go 1,2, or in other words, it'll be a direct addition. So a direct addition would leave us with this product. We're still not changing anything over here yet. And methanol. I'm going to write it as a minus right now, Sometimes we can use diethyl ether to be a source of an acidic proton. It's not very good at that. It's pretty bad, just as bad as an imide would be of a base. But it still can work. So if I wanted to draw this as its protonated form, that'd be fine too. And in fact, why don't I do that? So, here. So we're just going to write it as it's protonated. It looks neater. So from this point, we're now going to enter in, this is tert or tetra butyl ammonium fluoride. So tetra because it's 4, THF is just your solvent. And we know this, it's a weird mechanism, but it's the reagent that reduces TbSCl. So this will get our alcohol back. So getting our alcohol back, we're still in a wedge, we haven't done anything there. And there's your alcohol. And then the stuff that we need to protect from is over here. And it'd be just like that. So that's, I guess the end of 5 is the answer to D. So this is our full answers to letter C and letter D for this problem.